Ruthenium is a chemical element with symbol Ru and atomic number 44. It is a rare transition metal belonging to the platinum group of the periodic table. Like the other metals of the platinum group, ruthenium is inert to most other chemicals. The Baltic German scientist Karl Ernst Claus discovered the element in 1844 and named it after his homeland, the Russian Empire. Ruthenium is usually found as a minor component of platinum ores. The annual production is about 20 tons. Most ruthenium produced is used in wear-resistant electrical contacts and thick film resistors. A minor application for ruthenium is in platinum alloys and is a chemistry catalyst. Characteristics. Physical properties. A polyvalent hard white metal. Ruthenium is a member of the platinum group and is in group 8 of the periodic table, whereas all other group 8 elements have 2 electrons in the outermost shell. In ruthenium, the outermost shell has only 1 electron. This anomaly is observed in the neighboring metals, niobium, rhodium, and palladium. Ruthenium has 4 crystal modifications and does not tarnish unless subject to high temperatures. Ruthenium dissolves in fused alkalis to give rutheniates. RuO2-4 is not attacked by acids but is attacked by halogens at high temperatures. Indeed, ruthenium is most readily attacked by oxidizing agents. Small amounts of ruthenium can increase the hardness of platinum and palladium. The corrosion resistance of titanium is increased markedly by the addition of a small amount of ruthenium. The metal can be plated by electroplating and by thermal decomposition. A ruthenium-molybdenum alloy is known to be superconductive at temperatures below 10.6 K. Ruthenium is the last of the 4D transition metals that can assume the group oxidation state +8, and even then is less stable than the heavier congener osmium. This is the first group from the left of the table where the second and third row transition metals display notable differences in chemical behavior. Like iron but unlike osmium, ruthenium can form aqueous cations in its lower oxidation states of +2 and +3. Ruthenium is the first in a downward trend in the melting and boiling points and atomization enthalpy in the 4D transition metals after the maximum, seen at molybdenum. Because the 4D subshell is more than half full and the electrons are contributing less to metallic bonding. Unlike the lighter congener iron, ruthenium is paramagnetic at room temperature, as iron also is above its Curie point. The reduction potentials in acidic aqueous solution for some common ruthenium ions are shown below. Isotopes. Naturally occurring ruthenium is composed of 7 stable isotopes. Additionally, 34 radioactive isotopes have been discovered. Of these radioisotopes, the most stable are 106 Ru, with a half-life of 373.59 days, 103 Ru, with a half-life of 39.26 days and 97 Ru, with a half-life of 2.9 days. 15 other radioisotopes have been characterized with atomic weights ranging from 89.93 U to 114.928 U. Most of these have half-lives that are less than 5 minutes except 95 Ru and 105 Ru. The primary decay mode before the most abundant isotope, 102 Ru, is electron capture and the primary mode after is beta emission. The primary decay product before 102 Ru is technetium and the primary decay product after is rhodium. Occurrence is the 74th most abundant element in Earth's crust. Ruthenium is relatively rare, found in about 100 parts per trillion. This element is generally found in ores with the other platinum group metals in the Ural Mountains and in North and South America. Small but commercially important quantities are also found in pentlandite extracted from Sudbury, Ontario, Canada, and in pyroxenite deposits in South Africa. The native form of ruthenium is a very rare mineral. Production: roughly 12 tons of ruthenium are mined each year, with world reserves estimated as 5,000 tons. The composition of the mined platinum group metal mixtures varies widely, depending on the geochemical formation. For example, the PGMs mined in South Africa contain on average 11% ruthenium, while the PGMs mined in the former USSR contain only 2%. Ruthenium, osmium, and iridium are considered the minor platinum group metals. Ruthenium, like the other platinum group metals, is obtained commercially as a byproduct from nickel and copper, and platinum metals ore processing. During electro-refining of copper and nickel, noble metals such as silver, gold, and the platinum group metals precipitate as anode mud, the feedstock for the extraction. The metals are converted to ionized solutes by any of several methods, depending on the composition of the feedstock. One representative method is fusion with sodium peroxide followed by dissolution in aqua regia, and solution in a mixture of chlorine with hydrochloric acid. Osmium, ruthenium, rhodium, and iridium are insoluble in aqua regia and readily precipitate, leaving the other metals in solution. Rhodium is separated from the residue by treatment with molten sodium bisulfate. The insoluble residue, containing Ru-Os and Ir, is treated with sodium oxide, in which iron is insoluble, producing dissolved Troanose salts. After oxidation to the volatile oxides, RuO4 is separated from OSO4 by precipitation of 3RuCl6 with ammonium chloride, or by distillation or extraction with organic solvents of the volatile osmium tetroxide. Hydrogen is used to reduce ammonium ruthenium chloride, yielding a powder. The product is reduced using hydrogen, yielding the metal as a powder, a sponge metal that can be treated with powder metallurgy techniques or argon arc welding. Chemical compounds. The oxidation states of ruthenium range from 0 to +8 and -2. The properties of ruthenium and osmium compounds are often similar. The +2, +3, and +4 states are the most common. The most prevalent precursor is ruthenium trichloride, a red solid that is poorly defined chemically but versatile synthetically. Oxides and chalcogenides. Ruthenium can be oxidized to ruthenium oxide, which can in turn be oxidized by sodium metaperiodate to the volatile yellow tetrahedral ruthenium tetroxide. RuO4, an aggressive, strong oxidizing agent with structure and properties analogous to osmium tetroxide. Like osmium tetroxide, ruthenium tetroxide is a potent fixative and stain for electron microscopy of organic materials, and is mostly used to reveal the structure of polymer samples. Dipotassium ruthenate and potassium perruthenate are also known. Unlike osmium tetroxide, ruthenium tetroxide is less stable and is strong enough as an oxidizing agent to oxidize dilute hydrochloric acid and organic solvents like ethanol at room temperature, and is easily reduced to ruthenate RuO2-4 in aqueous alkaline solutions. It decomposes to form the dioxide above 100 degrees Celsius. Unlike iron but like osmium, ruthenium does not form oxides in its lower +2 and +3 oxidation states. Ruthenium forms dichalcogenides only when reacted directly with the chalcogens, which are diamagnetic semiconductors crystallizing in the pyrite structure and thus must contain ruthenium. Like iron, ruthenium does not readily form oxoanions, and prefers to achieve high coordination numbers with hydroxide ions in instead. Ruthenium tetroxide is reduced by cold dilute potassium hydroxide to form black potassium perruthenate KRuO4, with ruthenium in the +7 oxidation state. Potassium perruthenate can also be produced by oxidizing potassium ruthenate K2RuO4 with chlorine gas. The perruthenate ion is unstable and is reduced by water to form the orange ruthenate. Potassium ruthenate may be synthesized by reacting ruthenium metal with potassium hydroxide and potassium nitrate. Some mixed oxides are also known, such as MeRuVO3, Na3RuVO4, Na2RuV, 207, and Me2LanieRuVO. 6. Halides and oxyhalides. The highest known ruthenium halide is the hexafluoride, a dark brown solid that melts at 54 degrees Celsius. It hydrolyzes violently upon contact with water and easily disproportionates to form a mixture of lower ruthenium fluorides, releasing fluorine gas. Ruthenium pentafluoride is a tetrameric dark green solid that is also readily hydrolyzed, melting at 86.5 degrees Celsius. The yellow ruthenium tetrafluoride is probably also polymeric and can be formed by reducing the pentafluoride with iodine. Among the binary compounds of ruthenium, these high oxidation states are known only in the oxides and fluorides. Ruthenium trichloride is a well-known compound, existing in a black alpha form and a dark brown beta form. The trihydrate is red. Of the known trifluorides, trifluoride is dark brown and decomposes above 650 degrees Celsius. Tetrabromide is dark brown and decomposes above 400 degrees Celsius. And triiodide is black. Of the dihalides, difluoride is not known, dichloride is brown, dibromide is black, and diiodide is blue. The only known oxyhalide is the pale green ruthenium oxyfluoride, RuOF4. Coordination and organometallic complexes. Ruthenium forms a variety of coordination complexes. Examples of the many pentamino derivatives N+ that often exist for both Ru and Ru. Derivatives of bipyridine and terpyridine are numerous, best known being the luminescent tris-ruthenium chloride. Ruthenium forms a wide range compounds with carbon-ruthenium bonds. Grubbs's catalyst is used for alkene metathesis. Ruthenacene is analogous to ferrocene structurally, but exhibits distinctive redox properties. The colorless liquid ruthenium pentacarbonyl converts in the absence of CO pressure to the dark red solid triruthenium dodecacarbonyl. Ruthenium trichloride reacts with carbon monoxide to give many derivatives including RuHCl3 and Ru23. Heating solutions of ruthenium trichloride in alcohols with triphenylphosphine gives tris-ruthenium dichloride 3, which converts to the hydride complex chlorohydridotris-ruthenium 3. History. Though naturally occurring platinum alloys containing all 6 platinum group metals were used for a long time by pre-Columbian Americans and known as a material to European chemists from the mid-16th century, not until the mid-18th century was platinum identified as a pure element. That natural platinum contained palladium, rhodium, osmium and iridium was discovered in the first decade of the 19th century. Platinum in alluvial sands of Russian rivers gave access to raw material for use in plates and medals and for the minting of ruble coins. Starting in 1828, residues from platinum production for coinage were available in the Russian Empire, and therefore most of the research on them was done in Eastern Europe. It is possible that the Polish chemist Jedrzej Niedecki isolated element 44 from South American platinum ores in 1807. He published an announcement of his discovery in 1808. His work was never confirmed, however, and he later withdrew his claim of discovery. Johannes Berzelius and Gottfried Osann nearly discovered ruthenium in 1827. They examined residues that were left after dissolving crude platinum from the Ural Mountains in aqua regia. Berzelius did not find any unusual metals, but Osann thought he found 3 new metals, which he called pluranium, ruthenium, and polonium. This discrepancy led to a long-standing controversy between Berzelius and Osann about the composition of the residues. As Osann was not able to repeat his isolation of ruthenium, he eventually relinquished his claims. The name ruthenium was chosen by Osann because the analyzed samples stemmed from the Ural Mountains in Russia. The name itself derives from Ruthenia, the Latin word for rose, a historical area that included present-day Western Russia, Ukraine, Belarus, and parts of Slovakia and Poland. In 1844, Karl Ernst Claus, a Russian scientist of Baltic German descent, showed that the compounds prepared by Gottfried Osann contained small amounts of ruthenium, which Claus had discovered the same year. Claus isolated ruthenium from the platinum residues of ruble production while he was working in Kazan University, Kazan, the same way its heavier congener osmium had been discovered 4 decades earlier. Claus showed that ruthenium oxide contained a new metal and obtained 6 grams of ruthenium from the part of crude platinum that is insoluble in aqua regia. Choosing the name for the new element, Claus stated, "I named the new body in honor of my motherland, ruthenium. I had every right to call it by this name because Mr. Osann relinquished his ruthenium and the word does not yet exist in chemistry." Applications. Because it hardens platinum and palladium alloys, ruthenium is used in electrical contacts, where a thin film is sufficient to achieve the desired durability. With similar properties and lower cost than rhodium, electric contacts are a major use of ruthenium. The plate is applied to the base by electroplating or sputtering. Ruthenium dioxide with lead and bismuth ruthenates are used in thick film chip resistors. These 2 electronic applications account for 50% of the ruthenium consumption. Ruthenium is seldom alloyed with metals outside the platinum group, where small quantities improve some properties. The added corrosion resistance in titanium alloys led to the development of a special alloy with 0.1% ruthenium. Ruthenium is also used in some advanced high-temperature single-crystal superalloys, with applications that include the turbines and jet engines. Several nickel-based superalloy compositions are described, such as EPM102, TMS162, TMS138, and TMS174, the latter 2 containing 6% rhenium. Fountain pen nibs are frequently tipped with ruthenium alloy. From 1944 onward, the famous Parker 51 fountain pen was fitted with the Ru nib, a 14K gold nib tipped with 96.2% ruthenium and 3.8% iridium. Ruthenium is a component of mixed metal oxide anodes used for cathodic protection of underground and submerged structures, and for electrolytic cells for such processes as generating chlorine from salt water. The fluorescence of some ruthenium complexes is quenched by oxygen, finding use in optode sensors for oxygen. Ruthenium red 6+ is a biological stain used to stain polyanionic molecules such as pectin and nucleic acids for light microscopy and electron microscopy. The beta-decaying isotope 106 of ruthenium is used in radiotherapy of eye tumors, mainly malignant melanomas of the UVEA. Ruthenium-centered complexes are being researched for possible anti-cancer properties. Compared with platinum complexes, those of ruthenium show greater resistance to hydrolysis and more selective action on tumors. Ruthenium tetroxide exposes latent fingerprints by reacting on contact with fatty oils or fats with sebaceous contaminants and producing brown, black, ruthenium dioxide pigment. Catalysis. Ruthenium is a versatile catalyst, with an aqueous suspension of cadmium sulfide particles loaded with ruthenium dioxide. The energy of visible light can split hydrogen sulfide. This process may one day be used to remove H2S in oil refineries and other industrial processing facilities. Organometallic ruthenium carbene and alkylidine complexes have been found to be highly efficient catalysts for olefin metathesis, a process with important applications in organic and pharmaceutical chemistry. Ruthenium-promoted cobalt catalysts are used in Fischer-Tropsch synthesis. Solar energy conversion. Some ruthenium complexes absorb light throughout the visible spectrum and are being actively researched for solar energy technologies. For example, ruthenium-based compounds have been used for light absorption in dye-sensitized solar cells, a promising new low-cost solar cell system. Data storage. Chemical vapor deposition of ruthenium is used to produce thin films of pure ruthenium on substrates. These films show promise for use in microchips and for the giant magnetoresistive read element for hard disk drives. Ruthenium is also suggested for microelectronics because it is compatible with semiconductor processing techniques. Exotic materials. Many ruthenium-based oxides show very unusual properties, such as a quantum critical point behavior, exotic superconductivity, and high-temperature ferromagnetism. Bibliography. Greenwood, Norman N. Earnshaw, Alan. Chemistry of the Elements. Butterworth Heinemann. ISBN 0080379419.